everyone, my name is Alex and welcome to An Engineer's Findings. This episode is about the central lubrication system upgrade I did quite recently on my EMCO V13 lathe here, because so many of you guys commented in the last video about the fact that you wanted to see a dedicated episode about this lubrication system upgrade. So here it is, I hope you like it. So central lubrication systems in general, they should take care on our machines. Well, let it be a tractor, a truck trailer, a locomotive, maybe even a skiing lift, I don't know. So those systems should take care of all the little places on our machines that need lubrication. So that firstly, we save on our labor, because add up all those minutes in your life in which you tended an oiling port on some place and get the shock of a lifetime. So firstly, we want to save labor with these systems. And secondly, you know how human individuals are. They sometimes tend to forget stuff. Don't look at me. And sometimes people forget to oil places or lubricate stuff. And so central lubrication system should take care of that and prolong the lifetime of our machines, hopefully. Now, the upgrade here that I'm about to show to you is a very basic one, because I'm the only person operating this lathe. There are no employees here. And it's a very basic system with a hand-operated pump and some piston distributors here and there. And you can elaborate so much on these systems with electrical pumps, with timer circuits and so on. But I'm about to show you this basic functionality here and what I did in particular to the machine to fit everything together. And I want to touch a bit on the working principle, particularly on the piston distributors, because I get the impression that some people have a difficult time to understand what those do. So in case you're interested in these things, join me, why not? So what's the big benefit of all this, Alex? Well, here I feel hydraulic lock, even though if the pump wasn't connected the lever would travel further. But, well, now the whole machine is lubricated. Or similarly here on the WF1 mill, here I feel lock and the machine is lubricated. In my opinion, the most interesting aspect of a central lubrication system is the way how we divide the oil flow that comes from a central pump to all the individual locations that need lubrication. So on this particular machine I use piston distributors to do this. So here are, for example, 3 of them. Here on the tailstock are 6 more, and on the bed slide of the machine, hidden behind this sheet metal piece here, there is 6 more of those. And let me talk a bit about those piston distributors and how they work and what they do. So let's think of the machine that we want to modify with a lubrication system as having individual oiling ports, like in this example 1, 2, 3 and 4. In reality there may be many more, but that really doesn't matter. So from experience with the hand oiling gun, you may know that there are oiling ports which require a fair amount of force on the oiling gun to flow some oil into those. And let's say 1, 2 and 3 are restrictive oiling ports. And then there may be other oiling ports which require almost no effort to flow some oil into them, and let's say 4 is an easygoing one. Now what would happen if we connected those ports with one central pump that supplies a certain volume of oil per actuation? Then that volume would almost exclusively flow into the easygoing oil port or ports, and almost no oil would flow into the more restrictive ports. And of course that's something that we totally want to avoid, because rather we want every oiling port to receive a certain amount of oil regardless how restrictive they are. So that is usually done by using piston distributors in line. Now there's different technologies available. There's piston distributors, there's progressive distributors, but in my experience the piston distributors are the ones that are mostly encountered, so that's why I want to delve a bit into those. So this piston distributor here was made by Vogel in Germany. Vogel was a brand back in the day known for its high quality central lubrication parts. And Vogel later was sold to SKF, the bearing manufacturer, and SKF produces, to my best knowledge, these parts even today. Now this is one of my spare distributors, and for the sake of common good, dun, 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 I sacrificed it and machined away a quarter of its housing in order to be able to show to you its internals and hopefully be able to explain to you how those work. So here to that side is connected to the supply pump. So this is the intake port. And that brass piece here is the discharge port that supplies a metered amount of oil to the individual oiling port. Now we have individual parts here on the inside. Here, this piece, this rubber piston, is sort of a double check valve. So you see it moves in that fashion here. Then we have this turned steel piece here in the center, which is sort of like a tube. You can see it reaches from the screwdriver tip here to here, has a central hole that goes from here to there. And then there is this cross hole here. I hope you can see it. So this cross hole connects the inside of the tube with this chamber and with the discharge port. So let's think of all these three as one thing. And then there is this plunger piston here. You see this one that rides on that central tube. So this plunger piston has a rubber seal here and this return spring that moves it back into its position like so. So how does all that work? As pressurized oil is supplied here to the intake port, it moves that rubber piston. And take a sharp look here at the piston skirt and that shoulder here. And you see when I move the piston, the skirt ever so slightly opens the passage at this shoulder here for pressurized oil on the intake to pass that skirt and enter this chamber here. I almost forgot to mention, as this is the initial configuration, then think of this chamber, the discharge port, and all the way to the oiling port, everything filled with oil, the center of the tube, and all the supply lines filled with oil. So oil comes in here, pushes this piston, opens the piston skirt to that side, so that's the first check valve function. And the rubber face of that piston closes the hole of the tube here. So that is the second check valve function. So it pushes that piston to the side. Now oil that is supplied flows past the rubber piston skirt into that chamber. It cannot escape through the hole in the tube because the hole in the tube is closed by the rubber piston. So next best thing it can do, since more and more oil is supplied, is push that piston to the side. So in essence, as the plunger piston is moved to the side, oil from this upper chamber here is pumped by the piston to this cross hole, to the inside of the tube, to the discharge port, and from there to the lubrication port of the machine. And this pumping action happens until the piston reaches its upper end stop. And that is when this shoulder here hits the brass piece up here. So whenever that happens, you see we can keep supplying pressurized oil to that piston distributor, but nothing further will happen because the piston is in its end stop and the check valve piston will keep the transfer tube closed. There may be other piston distributors at this very moment still moving on the machine, but that doesn't matter for this distributor And even if we increase the pressure to this piston distributor, it will continue to stay in somewhat of an hydraulic lock until we let go of the pump and pressure on the intake of the piston distributor falls. Then what happens next is that this return spring forces the plunger piston back into its initial position, and thereby oil from this lower chamber pushes the check valve piston back into its seat and thereby opens this intake hole on the transfer tube as a passage for oil from that chamber to move to the intake, to the transfer tube, to the cross hole and into the upper chamber. So on the return stroke, what happens is that oil from this lower chamber that was previously used to push the piston upward is now refilling the upper chamber. And you see, now we're back in the initial configuration of that piston distributor, and we are ready for the next lubrication cycle to happen. That will be whenever we decide to operate the pump again. So in essence, this is how those piston distributors work. Now there's two things to note here. The one thing is that the discharge volume from the piston distributor is clearly a function of how far that piston can travel. Now, why is that important? So you see, this particular one is a 0.16 cubic centimeter discharging piston distributor. And you may be a cheap guy like I am and source stuff like this from the used market. So you see, it is really no bummer if you can only source discharge volume types that do not fit your desire, because the only difference they have, if they have the same housing, is that the brass piece may have a protrusion on the inside that limits the piston travel. Or there may be a bushing on the inside to limit the piston travel. So let's say you wanted to decrease the discharge volume of this particular distributor, then you could machine a bushing that fits on the inside here that limits the travel of the piston. Or if you have a lower discharging piston distributor that has a protrusion on the brass piece, for example, you can machine that away and give it more discharge volume thereby. And the other thing that we can learn from this is that the whole metering function of these piston distributors is only given if we can make sure that their pistons hit the end stops. So you see, we have to make sure that the volume that our pump supplies is enough to move all the piston distributors that we have installed on the machine to their end stops. And the pump must supply all that volume in one shot. So you see, we have to size the pump accordingly so that all the piston distributors on the machine can do their job. So coming back to our V13 lathe example now, the pump that I have can supply 15 cubic centimeters volume of oil with a full pump stroke on the lever. So let's check how much volume we're consuming. On the cross slide, I have installed 2.6 cubic centimeter distributors. Those supply the sliding surfaces. And I have 1.2 cubic centimeter. So if we add all of those together, we get a required oil volume of 4.2 cubic centimeters total per stroke. So you see, with the pump that we have, we can easily live with that, and we could even add more piston distributors safely to the system if we decided to do so. So just as a graphic representation of how much volume that is, so this syringe has 20 milliliters or 20 cubic centimeters, that's the same thing. So the pump can supply up to 15 cubic centimeters with a full lever stroke, so that's that much volume of oil. And for example, one sliding surface on the cross slide gets 0.6 cubic centimeters, which is roughly that amount of oil. So the pump I have installed here on the lathe is an SKF POE-15-05. The 15 means that it can discharge up to 15 cubic centimeters of oil with a full stroke on the lever. The 05 means the bucket takes up to half a liter of oil. And I got this as a new old stock component from the used market, and you see it already happening on me. This is where plastic parts are really not nice on new products, because what happens with this one is so please, you designers out there, give us a break. And that's why I usually don't close down this lid all the way on this particular pump here, because it tends to jam and then the lid piece comes loose from the bucket piece. But nevertheless, so I got this from the used market and it was missing these strainers here. But you know, the dump ones are usually the lucky ones, and I found that these T-eggs exactly fit the throat diameter on that thing here. And as a quick note on the pump that I have installed on the lathe, check out this schematic of how it hydraulically functions. So we have the bucket with the strainer, bucket holds the oil, oil is fed to the inlet of the hand operated piston pump. Here's the handle. But what's all that other crap here? Well, you see, the pump pressure here opens that valve, or pushes the valve to the side, so that we have free passage for oil to the outlet, and from there to all the piston distributors. So whenever we let go of the handle, pressure here falls, valve returns into the position as shown, and our line pressure can relax because the line is connected back to the tank. Now that's an important feature. However, I'm not sure if this is a discrete part or assembly in that pump. I rather believe that this valve function is implemented by some cross holes in the cylinder of the piston pump here. But be that as it may, all I'm trying to say is our pump must relax the line pressure whenever we do not operate it for the piston distributors to work correctly. And this thing here is just the pressure relief valve that limits the line pressure, in this case here with that pump, to 30 bars. So whenever all our piston distributors have reached their end stops and we keep brute forcing the handle, this valve makes sure that we do not rupture a line or damage a seal or what have you. So as I was mentioning, the lines, the lines I used are SKF high pressure lines with 4mm diameter. They're out of PA12 and have a bursting pressure of, wouldn't you believe it, 21 megapascals. That's 210 bars. Now the pressure relief valve on our pump is calibrated to 30 bar in my case, so that's plenty strong lines for our purpose. I wouldn't dare to use pneumatic line instead, because I think we quite regularly reach that 30 bars, and I think pneumatic line wouldn't be able to cope with that. So that's why I use high pressure line here. I'm not sure about the ultraviolet stability of those lines, but I'm sure they are also available in black color in case you have something that's on the outside of the workshop. So what about the fittings? Well, the fittings I ordered from this company in Germany, I just mentioned them because they are quite friendly and they have a good selection of parts, I think. So those fittings are push-in style, like pneumatic fittings. However, they are high pressure, so they work up to 80 bars. And they come in various thread sizes and angles. Those here, for example, are M6 threaded fittings. And the threads usually on those are conical, so that You just have to drill and tap an M6 hole on the machine, thread this one in, and they're usually pressure tight without any big hassle. So as I said, they're push-in fittings and work like this. And whenever we want to reopen it, we just push down on that ring and our line comes out again. Now I wanted to mention that I usually chamfer the lines slightly with the knife before I insert them into those fittings, because I'm a bit afraid of that hard plastic damaging the seal on the inside with those sharp edges from cutting the line. So every project starts with this assembly, I guess. So you see the cross slide linear scale already taken off, compound rest taken off. You see the cross slide disassembled from its nut here so that it can be slid back and taken off eventually. And let me point out the original lubrication ports in this picture. So there was one here that supplied this hole in the cross slide lead screw nut and the threads of it. This one here supplied, in theory at least, the flat bed slide. This one supplied the prismatic bed slide, and to the side here there was one port that supplied the rack and pinion drive. So you see, not really overwhelming, but reason enough for me to do this modification here. And at this point of the project, I made a call that I didn't want to add fittings and lines for the lubrication system up here at these ports and route the lines to the back and such, or even worse, a fitting here and routing lines to the back, because all of this would be a big obstacle in the working area. These lines would collect dirt and chips and would be difficult to clean. So rather, I wanted to have all the connections for the bed slide lubrication on the back here, hidden out of the way of the work, so that eventually this modification would be an upgrade and not just a, well, change. So that rack and pinion drive down here was a slight tough nut to crack in terms of lubrication. So you see in this picture I'm using this paper template to check where the wall is and whether or not I could fit a lubrication hole here that would supply the rack and pinion drive from the top piece that is here on the bed slide. So you see this paper template inverted on here and located with those two bolts. And indeed there was enough overlap of those two walls to be able to fit an O-ring here and a transfer hole, if you will. However, there was not a lot of room for error, but I must say fortunately that worked out nicely in the end. These pockets here, I freehand milled those a few years ago, because originally oil coming in through that port here would just flow out through that slot to that side and that side of the bed slide, and there was really a minimal chance of that oil wicking into the sliding surface gap. So sooner or later I milled those slots into there to give the oil at least a tiny chance to wick into that gap. But those pockets, they are history now. Meanwhile, they are filled with whey epoxy on my machine, and I machine proper lubrication pockets into these sliding surfaces, as you will see in a minute. Those scraped oil pockets up here on the cross slide, they were not original. I made those when I corrected the right angle error on the cross sliding surfaces, but that's a different story. So my plan at this point was to drill some holes into this piece. One hole going in from the back here and going to that depth and supplying the flatbed slide. Then a second one coming in here and going all the way to that depth and supplying the prismatic bed slide. And then a third one going in here and reaching all the way to this depth here roughly. They're meeting up with the transfer hole that would eventually supply oil to the rack and pinion drive. Or at least I did hope so. And because I didn't want those holes to have large diameter, because I didn't want to take away too much cross section of that cast iron piece, I wanted those holes to be 2 millimeter diameter, so you see there was absolutely no chance for me to drill those holes myself. So eventually I brought this piece to a company that EDM drilled those holes for me, and when I questioned them about the tolerances of the location of the bottom of the hole, they said they cannot guarantee for anything, they will try the best and so on, but eventually I will have to see. And you can imagine how thrilled I was when afterwards I drilled those transfer holes, hoping that I would hit the bottom of these EDM deep holes. Thrilling to say the least. So you see, this was a quite critical step in that whole modification process. And in order to minimize the room for positioning error of those holes, or at least to move the room for error to my side, I decided to pre-drill those holes so that the EDM company would have something to center up upon and wouldn't have to use numbers. So I clamped the piece in the mill and used the horizontal spindle to pre-drill those holes. So you see 1, 2, and 3. And here they are already tapped for M4, because later on they will get plugged with an M4 set screw. So I would supply those deep holes through a fitting on the bottom of the piece here with a transfer hole feeding the deep hole and then feeding the respective lubrication port. These were the instructions that I sent to the EDM company, and you see that one hole here, the deepest one, having a depth of 286.5. That means a depth of more than 140 times the diameter. I'm not sure if that classifies as a deep hole. What do you say? With the bed slide top piece at the EDM company, I had some time to focus on the bed slide gearbox, which, as you can see from the picture, showed all those places with 35 years worth of grit and grime, places that usually cannot be reached for cleaning. So this was also a good opportunity to get rid of this mess. And I was particularly astonished to find how many chips had found their way into the relieved spaces in the clasp nuts. So also a good point in time to get rid of those. With the cleaned gearbox, I started to drill the transfer hole that supplies oil to the rack and pinion drive. So the pinion is here with its drive shaft going to the inside of that gearbox. And originally this was supplied through an oiling port here and a hole in that rib. Now this is all blocked off and plugged in my case. So here you see that hole and the cleaned up gearbox, and the inspection showed that everything is nice and neat for further service. And in order to make sure that the location of that hole is properly transferred to the top piece, I made a bluing transfer where I blued the surface and then assembled those two pieces. And here is the result of that bluing transfer, so you can clearly see this is where the hole should go. So I drilled this hole here. This is the top piece of the bed slide back from the EDM company. So with the deep holes already in it. And you can imagine how thrilled I was when I drilled that transfer hole, whether or not I would be hitting the deep hole. And tell you what, I didn't hit anything at first. So I drilled 2 millimeters deeper than planned, but I still didn't hit that deep hole. And I thought, well, now all that money for the EDM hole drilling is wasted. But then I realized that I made a mistake by blue transfer that hole location, because that set me off maybe 0.5 millimeter up to 1 millimeter from the location that I implemented by pre-drilling that deep hole here. By following the bluing method, I put myself off of the axis of the deep hole, and the deep hole was very exact. And after I realized this, I decided to drill that hole a bit larger. So this is, I think, 3.2 millimeters in diameter. as opposed to 2 millimeters, and that helped breaking through to the EDM deep hole. And you can imagine how relieved I was. And this pocket here is for the O-ring, so that the transfer hole would be tight when bed slide and the top piece would be assembled. And the tape measure is supposed to give you an idea of how deep that hole is, 2 millimeter diameter. So with that hole successfully taken care of, I can finally start concentrating on the slide surfaces and machine proper lubrication pockets into those. So you see in this picture, the old lubrication pockets are already filled with whey epoxy, and here I'm using the circular level to level in to this particular sliding surface. And you see I used the ball end mill to machine those pockets here, and here I adjusted this sliding surface to be slightly off angle of the cutter axis, so that those kind of wedge shaped pockets are created. And this is all on purpose because I want these pockets here and here to end before the contact with the bed slide ends. This is supposed to prevent that oil just drains into the chip tray, but rather I want oil to stay in these pockets as long as possible, so that the oil has a chance in regular intervals of wicking into the sliding surface gap here. Here a picture of machining the oiling pocket on the flat slide, and you may have noted that I use a ball end mill to do this, so that the pocket kind of softly transitions into the sliding surface. That way there is sort of an oil wedge, and an oil wedge, whenever the bed slide is moved, contributes with hydrodynamic lift, so that the chances of the sliding surfaces having metal on metal contact and wearing away, those chances are lessened. And I couldn't help it, I had to re-scrape the slide surfaces because I couldn't look at them anymore. And as a tool for bluing, I used the bed slide on the very right end where the tailstock usually rests. You can see how the epoxy filled old lubrication pockets are now nicely scraped with all the other surfaces. That was a nice meditative work for a change. And then I had to decide where to mount the piston distributors and how to route the hoses. So you see those three, 1, 2, and 3, they connect to the bottom of the top piece of the bed slide, for which we drilled the holes just recently. And those 3, they supply the cross slide, about which I'm going to talk in a minute. And this is all the stuff assembled. Now let's take a look at those ports here. On the cross slide I wanted to create 4 new lubrication ports. So that is 1 + 1 supplying oil to the coplanar surface pair, and 1 + 1 supplying oil to the tilted slide surface pair, those 2. So obviously, also because I wanted to connect from the back side, that required deep holes, 1 here, 1 here, and transfer holes to supply those locations. And we needed a 3rd deep hole supplying oil to this former lubrication port that supplies the cross slide nut. So I had these holes also EDM drilled, and in order to avoid positioning error, I pre-drilled those holes as well. You see 1, 2, and 3 here already drilled and tapped for M6, because I will fit lubrication fittings directly to those holes. Here are the instructions for EDM drilling, and you see a depth of 175, that's not so bad. EDM drilling is a really nice business, I must say. I had no problems whatsoever hitting the bottom of these holes with the transfer holes. So you see the transfer holes 1 and 2 here are already drilled. This other deep hole is already broken through to this transfer hole, this original transfer hole, so we don't have to do anything here. In a similar fashion as on the bed slide, I machined the lubrication pockets, and they end abruptly here on the slide because I don't want them to be uncovered whenever the slide is driven to its extreme positions. So this required some careful planning to make sure that those passages stay covered all the time. I also drilled transfer holes from the outside. You see one here already plugged with an M4 set screw. The second one would be here and the transfer hole going that way. So this transfer hole connects the deep hole with this slot here. And here I'm machining those wedge-shaped pockets, also with angle offset between the sliding surface and the end mill axis, so that oil can wick into those surfaces nicely. Here you see that when assembled, so one transfer hole feeding oil to that slot and down into these pockets to wick on the sliding surface, and the same here, transfer hole and the pockets. On the other side, the gib is in contact with the bed slide top piece, so that requires some pockets in the gib as well. These are just filed. So you see the finished cross slide and the gib. Moving on to the tailstock, at this point in time I also made the call that I wanted everything hidden away on the back side of the tailstock as much as possible and out of the way of the work. So this required a fair bit of planning ahead, because for example the hole that supplies oil to the quill of the tailstock has to pass through a rib on the inside of that casting, and I had to make sure that I wouldn't hit air on the inside. Also, I wanted the lubrication system to keep functioning regardless if I had the tailstock adjusted for taper turning all the way to the end stops, of course. So that required machining of oil transfer pockets on the bottom of this casting here to transfer oil from this piece to the bottom piece. And you see, this is conventional deep hole drilling, really unspectacular in comparison to the bed slide, but still, this is conventional. So you see that deep hole starts here and ends at this transfer hole. So then we have this transfer pocket that delivers oil to the bottom piece of the tailstock, regardless of how they are adjusted in terms of taper turning. Also, the second oil transfer pocket here, the hole supplying it with oil from the outside starts here and joins the transfer hole here. The layout of the location of those pockets was a bit of a nut to crack, because you see the overlap of this top casting with the bottom casting is not 100%, and I had to make sure that firstly we are not breaking through to the outside and that we are not hitting an area where the bottom piece has no wall, for example. So the transfer pockets on the bottom piece, and here I'm drilling the hole from the transfer pocket down to the flat tailstock sliding surface, and this one here supplies the prismatic tailstock slide surface. In contrast to the bed slide, on the tailstock I decided to machine right-angled pockets, so using a conventional end mill, and that means losing hydrodynamic lift whenever you're moving the tailstock. But I wanted these pockets to have sort of a way wiper quality to them. Because, well, at least to me it regularly happens that whenever you push hard on the tailstock, it sometimes lifts away from the bed. You know, whatever you may call this here. It happens. And thereby there is a risk that some dirt gets underneath here. And I wanted to give this dirt a chance to get caught by a lubrication pocket before it wears all the length of the tailstock slide surface. The lubrication pockets on the prismatic slide surface are pretty much the same thing as on the bed slide, leveling in with the circular level and then machining these ports that are shorter than the contact patch with the bed slide, again to prevent oil from draining down. And in order to prevent oil from draining to the front and to the back, I drilled a hole here and one here that receives a plug, a plastic plug here, to close this passage for oil and to keep oil on the inside as much as possible. When I look at these surfaces, I will have to scrape this base sooner or later. So this is dry fitting the piston distributors and drilling and tapping the holes for the lubrication fittings. Now the hand wheel and shaft part of the tailstock I modified a bit. You see with these passages here, these oil passages. Also the shaft here received these passages. So that here is the axial ball bearing that receives the thrust from the tailstock, and oil from the upper lubrication port hits that bearing, and then I wanted this oil to be able to drain to some place so that the inside behind the quill wouldn't fill up with oil over time. So whenever the oil level reaches the height of that cylinder on the shaft, it would drain through these holes, these passages, and these passages to the outside, and thereby also lubricate the center bronze bearing on this cylindrical portion here and the face of this ring here. Here is a view on the inside of the tailstock casting, showing you that rib through which I had to drill a passage so that oil can reach the quill from the outside. So that required a bit of planning that I wouldn't miss this rib here. And then I made this oil manifold here that is connected to the pump, and then allows one fitting that leads to the tailstock, one to the bed slide, and one to the lead screw piston distributors. So here everything assembled. You see on the bottom this manifold piece, and the connection of the tailstock is through this line here that is U-shaped whenever the tailstock is in the right end position. And whenever we use the tailstock and drag it to the left, you see here I have this rotation fitting that allows this line to stretch a bit whenever we use the tailstock and to fold up in this U shape whenever the tailstock is in the parking position. And this bolt here just makes sure that this doesn't rotate to the left too far, because then that function wouldn't work anymore. Moving on to the bracket that holds the right end of the lead screw here, I drilled and tapped these holes, this one here, 2, 3, and these 3, so that we have sort of an L-shaped passage of oil into these bearing points. This one in the back here gets later plugged with an M4 set screw. So here 1, 2, 3, 4, 5, 6 holes. And you see here plugged with a set screw, so the lubrication fitting goes in here. Oil is routed to the center bronze bushing, and I also machined this slot in here so that the oil can wick nicely all the width into that center bronze bushing. Then I also modified the back wall, because when I test fitted the pump and gronked down hard on the lever, the back wall flexed a bit too much for my taste. So it's just a stainless steel sheet metal piece that's riveted onto the back wall with countersunk rivets, and some M4 screws down to the base so that it is nice and rigid now, but still the back wall can be disassembled off the machine nicely as it was before. Here from the back, these are the bolts that hold the pump. That fitting here I made so that we can connect the pump through the bottom of the back wall with the lubrication manifold. You see here the stiffener and the original holder of the back wall in the assembled state here. Now tell me, what do you think? Will this improve the lifetime on the machine? Never before could I move the bed slide on this one. With one finger, easy. And that's the old pockets. So that's it. Thank you very much for your interest in this video, guys. I hope you find the one or the other thing useful, and I'll see you on the next one. Bye!